Okay, so guys, we're going to start logistic regression now. And what it's used for is when you have something you're trying to predict, a y variable that's a yes-no variable, an all or nothing outcome. Like if you want to predict whether somebody's going to live or die, whether they're going to pass a course or not, get an A or not. Any yes, no prediction where there's just a binary outcome, a 1, 0, 0 y variable that we're trying to predict is when we're going to have to, we can't use our ordinary linear regression. We have to tweak things, and that's what logistic regression is all about. So far, all our y variables and all the predictive models that we've been looking at have been quantitative, like we're predicting your final exam score or the number of drinks you have, or just some quantitative y variable. But now we're going to look at y variables that just have two outcomes. So we're going to represent y will always just be a 0, 1 variable. So far only x's have been 0, 1 variables. Now y is going to be a 0, 1, and x can be either 0, 1 or quantitative. So when you think about that, when you're going to predict a 0, 1 variable, really what we want to do, the best we can do, is predict the probability of getting a 1, like the probability of getting accepted to med school. That's what we're going to be looking at in this data set. Okay? And you'll see why we're going to have to do something different than our ordinary least squares linear model. Okay, so here's an example that shows the MCAT biological science scores on the x-axis right here. I think they range from 0 to 15, but in this group they ranged from 6 to 12 to 14. Nobody got a 15, I guess. And these are 55 students at a Midwestern university, okay? And here, they either got accepted, in which case there's a 1 here. There's 55 students here. You can't see them all because, for example, right here, there were 4 people who got a 12, and there were 3, 1, 2, 3, that all got accepted, and 1 that didn't. I'll show you the, we can look on our data program and you can see the 55 people better. But so here, in fact, why don't we do that right now? Okay, so everybody either gets they either got accepted, in which case they get a 1, or they didn't. So let's go and I can show you what this looks like. And where we get this, if we just did our ordinary least squares, we'd get this equation. And it doesn't really make sense. Okay, so let's go to our data set here. And here we are, and on the x-axis we have our biological, this is real data by the way, biological science score. And on the y-axis, whether it got accepted or not. And why don't I just put a little jitter around this so you can see the separate data points. Okay, so now there are 55 points here, and when we fit this regression, it's going to first of all, how do we even fit this regression? So one way you can think about how this line was fitted is if you look at the this regressigram here, which, for example, in any vertical strip, for example, here's the vertical strip, there are 4 people who got a 12 on their biological science test, and 1 didn't get accepted, and 3 did. And so what this little horizontal line is the average of 3, it's 75% of the people got accepted. So this right here should intersect at 0.75. And so what we usually So within each vertical, like here, the people who got 6s, none of them got accepted. And the people who got 13 and 14, they all got accepted. And so what our usual regression line is the best fitting line through these horizontal, little horizontal strips here. That's what that is. But you can see that it really doesn't make sense. So we get these coefficients. Let's go back to our notebook. And when we make predictions for them, you can see that it doesn't really make sense because it predicts probabilities. Like if you extend this line in a range that we're interested in, you get probabilities greater than 1 or 100% and less than 0. I mean, we can do it for 10. It makes sense, but not for 6 and 14. I'll show you what I mean. So here we're using this predicted probability of getting accepted here. Probability of getting accepted is just a linear equation, and it's negative 1.263 plus 1848 times the biological science score. So for somebody who got a 10, here we get 0.585 or 58.5%. Well, that makes sense, but look what happens for somebody who gets a 6. You can see this line's going to go, we're going to make a negative prediction, right? So if we do the same thing here, and instead we plug in a 6, we get a negative probability. Negative 0.154 or negative 15.4%. And that's crazy. And same with 14. We plug in a 14 right here for the biological science score, we get 1.432 or 143.2%. So it doesn't make sense because we know that probabilities, this doesn't work. So because we know that probabilities have to be between what? 1 and 0 or 0 or between 100% and 0%. All right, so we have to do something else. Okay? So what are we going to do? How can we fix this problem? We probably see when I showed you the program that actually we could do a much better job by fitting a curve, okay, instead of a line. So we want to fit a curve. An S-shaped curve, I think I can show you on, let me go back here. So we want to fit more of a curve, and if we go to 0, 1 scatter plots, and we can do this, choose the y variable of acceptance, and this is just a program you can play around with, and biological science score here. Okay, we get this same, if we do the regression, we get that same line, but if we do a logistic regression, we fit this curve here. This very nice S-shaped curve here, okay? So let's look at this curve and think about why it makes sense. All right, so let's go back to the document camera here. So what do we want? We want a curve right here that's bounded, that the y-axis can't go over 1. So we want it bounded here. And it can't get to be less than 0, the y-axis. The x-axis, in this case, we just have positive x, but we could have a negative x. So we want it to look like this, right? And so we want this S-shaped curve, similar to the one above. And the most commonly used one is called the logistic curve, the logistic regression curve. And logistic regression is based on this curve. but there's lots of, first of all, there's lots of curves that have S shapes. There's lots of curves, many curves with S shape, similar to the one above. In fact, if you think about it, any curve of this form will have this, any curve of the form y is equal to some function of x over, increasing function of x in this case, over 1 plus f of x will work, right? And the logistic regression curve, the logistic, where f of x is positive, the logistic regression curve has this form. The f of x is e, is an exponential function, e to the beta plus beta 1x. It's linear in this exponent up here. And this is going to, you'll see why this is important. But that's the equation for logistic regression when you just have one x. We're going to look at multiple x's, but for today we'll just concentrate on one x. Okay? And of course, can this equation ever yield a probability greater than 1? Can it? No, because look, this denominator is always, the numerator is always less than the denominator. No, because the numerator, that's the numerator, is less than the denominator. So it can never get greater than 1. Can it ever yield a probability less than or equal to 0? Can it ever be negative? No, because e to the anything has to be positive, right? No, because e raised to any power is always going to be greater than or equal to 0 for all x. Think about it. Even if you have a infinitely negative x, it's going to approach 0 but not get close to it, right? So e to the x, the limit of that is x goes to negative infinity, is just going to equal 0. We'll get a tiny, tiny number. It'll get close to 0. So yeah, so that works. But it has a nice feature too. It has a really nice feature that that this exponent up here is linear, and we like linear equations, right? And so that if we take the log odds form, it will be linear here. Let me show you. So this curve has two nice features, and this is the reason why we use it. We just saw that it yields probabilities between 0 and 1, right? We just saw that, right? And now we can transform. Remember transformation of variables. We can transform the variable p, which is what we're interested in, the probability that, let's say, some cancer treatment or some medicine is going to save your life or not, yes or no. We're interested in the p probability, and we can transform that variable to something called the log odds, the log of p over 1 minus p, which is linear in x, allowing us to continue using many of the methods we developed for linear models. All right? So this log odds equation, this is called the log odds equation, is very familiar. It's just a simple linear equation. If you have 1x and if you have more predictor variables, it'll just be a multiple linear equation. Okay? So we have these three equivalent forms. This is the one we're interested in. This is that S-shaped curve we just talked about. This is what we're interested in, the probability of, here's the S-shaped curve. And that, as we saw, is bounded between, the y-axis is bounded between what? 0 and 1. And it looks like something like that. Of course, that means as x gets bigger, the probability of success gets bigger. So in this case, as your biological science score gets bigger, the probability of getting accepted into medical school gets bigger. But you could also obviously have it the other way, right? Just have it flip that way, and then what would that mean? That would mean as x gets bigger, for example, the number wrong you get on the biological science test, as that got bigger, then your probability of getting into med school would get less. So it can go either direction. So this right here is our S-shaped curve. Then we look at this odds form, which is P. Many of you who gamble are familiar with odds, right? So you can change a probability into an odds form. Like you could say you have 2-to-1 odds. If it's a 50-50 chance, you'd have 1-to-1 odds. So if you have a 50%, you'd have 1-to-1 odds. So it's basically the probability of success over the probability of failure, P over 1 minus P. And when we do that, you take this P right here, and if you divide it, this is just simple algebra, by 1 minus P, right here, if you do that, divide it by 1 minus P, and simplify it, that's what you get. You get just an exponential curve right there. And okay, so you get this exponential curve, and it's going to look like what? That's going to range from 0 to infinity. And it's just an exponential curve. So you would have from, draw it here, so from 0 to infinity, right? So this is an S-shaped curve, and this is an exponential curve. And it's P over 1 minus P. All right. And now, then what do we do with this? If we then take the log of the odds, if you take the log of the odds right here, the log of the odds, that's just the exponent up there. And now we have this nice linear equation that ranges from what? Ranges, it's a linear equation that would go from what? Here, if you have 0, it's going to go from negative infinity to positive infinity. And that's just a line. So that's the, we're going to get estimates for our parameters here using a similar method we do for linear regression. And then we're going to work back and forth between these forms and use those to then get this, to get a predictive model for a good predictive equation for the probability. So that's, and build confidence intervals and do the whole shebang that we've been doing. All right? So that's pretty much the idea. And I skipped that. So we should be on page 171 here. All right. And but before we do that, let me just give you an eye clicker to make sure that you understand where you should use, when you should use logistic regression and when you can't use it. So let's go over to the PC and go here. All right, so I just want you to think about this is just back to chapter 33, the very beginning, page 167, where we said, do you think you can use logistic regression? Is it appropriate to use if I wanted to predict, let's start with the first one, eye color from hair color? A, yes, B, no. Just what do you think? Okay, so just Is this an appropriate situation to use logistic regression? Yes or no? Let's see what you think. What did you say here? The answer is no, and most of you got that. Why? Anybody want to explain why it's not appropriate here? Is this y variable? Can you answer it with a yes/no question? What's your eye color? Can you say, can I divide it into yes and no? If I said blue eyes or not, it would be appropriate. Okay, you got it? All right, let's look at the next one. All right, let's do the next one. Let's start it. Predicting year in school from age. Everybody should get this. Actually, this is taken straight from an exam, this question. So, okay, I'm going to stop it soon because it's all just 20 seconds and we'll stop it. I don't want to. All right, let's see. No. Year in school. Can I say, can you answer that yes or no? What's your year in school? It's only yes or no questions that we can code as yes or no. If I ask you what's your year in school, can you turn that into a yes or no question? No, you can't. So do you understand why that's not appropriate? Come on, let's start doing better on here. Okay, I want everybody to get this next one right. Predicting passing the final from class attendance. Okay, I'll stop it right now. Let's see what you said. It's yes. Good. Good. I'm going to, whoops. There, you got a preview. Okay. Passing the final is yes or no. So yes here too. Both of these are going to be yes. Let's do this last one. Predicting log of children's income from the log of their parents' income. That would be something we'd probably have to, that would make sense to do. Is that a case of logistic regression? Yes or no? Okay, I'll stop it at 20 seconds. And no, it's not. Good. No, it's not. That's not a yes, no. That's not a binary y variable. That is a logistic transfer. That's a log transformation. That's not logistic regression. Don't get those two things confused. All right. Now, let's go back to the document camera here. And so this log of p over 1 minus p is the log odds, and p over 1 minus p is the odds. And it's the probability of success over the probability of failure. For example, if your odds are 4, that means the probability of the event occurring, success, is 4 times that of the event not occurring, failure. People call that 4 to 1 odds. So if your odds are 4 to 1 odds, let's just think about it. So 4 to 1 odds means what? Means that you have 4 successes to 1 failure. Maybe I should do it here. So look at this p over 1 minus p. What are we doing here? So let's define p as what? Let's say the number of successes, and success, just one of the outcomes we're going to call success, and the other one we're going to call failure. We have a binary, we have 2 possibilities. There's no other possibilities. Okay? So we'll call one of them success. And the p is going to be the probability of success over what? Total number of outcomes. Total number of possibilities. Right? Total number of, that says outcomes. And then you have 1 minus p, which is the number of what? Failures. failures over the total number of outcomes. Right? So we can cross those off, and we have the number of successes over the number of failures. That's how you can think of it. The number of successes over, so 4-to-1 odds, you can think of it as 4 successes for 1 failure. Okay, that ratio. So now that we think of that, what's the probability of success? The probability of success is the total number of successes, right, this, which is 4, over how many outcomes are there altogether? 4 plus 1, 5. So this is your success, the numerator's the same, and this is the total number of outcomes, which is just the numerator plus the denominator. All right, so what if your odds are 1 to 4? What would that mean? What would that be? 1 to 4 odds would mean what? Means 1 success over 4 failures, right? Which means P is equal to 1 over what? Your probability is 1 over what? 5. All right, so why don't we do this one as an iClicker now? So if your odds are 1/2, what's P? All right, so we'll just go back. All right, so now we're on page 34, chapter 34, page 171. Let's start this. So here, your odds are 1/2. What's P? Okay. Stop it now. And what is it? 1 over 1 plus 2, right? These two, so it's 1/3. It's B, right? Does everybody understand that? Let's see what you answered. Great, good. Okay, so let's just do the next one. Now, what's that one going to be? Okay, we'll stop it for a few seconds. Okay, and that one's going to be 2 over 3. Great. Okay. Terrific. All right, so let's go back to the document camera, and so let's just write that down. So you say odds equal to 1/2. That means what? That the probability is equal to 1 over 3, right? And if your odds are equal to 2 over 1, that means your probability is equal to 2 over 3. So if your odds are 2 over 3, then your probability is going to be 2 over 2 plus 3, which is 5. So this is, so let's just fill out this chart here, and it will help you just give you familiarity with, I just want you to have this become like almost muscle memory, because it's just so widely used, and it's just so that you just don't have to think about it, basically, and don't have to go back and forth this way. It's just cumbersome. Just can do it much more easily than that. Can just see right here that, for example, you'll see, okay, odds form is P over 1 minus P, and now the probability form, the probability you're going to see is that P is equal to odds over 1 plus odds, which is what we've been doing, right? Because any fraction can be put over 1. That's exactly what we've been doing. Okay, so let's look here. And now let's fill out this. We're not going to fill out the whole thing here, but we can start and see a pattern. Okay, so let's just start right here. So if your probability is 1 out of 100, then your 1 minus P is 99 out of 100. And what's your odds? Your odds are what? 1 over 100 over 99 over 100, which is 1 to 99. And then the log odds, you'd have to do that on the calculator, and that is approximately negative 0.46. Okay, now let's look over here. So if your probability, I just made it symmetrical. So if P is 99 over 100, then 1 minus P is 1 over 100, because they have to sum to 1, right? And now what's your odds here? Not 1 over 99, but what? 99 to 1. And now, your odds, so if we take the log of the reciprocal, what are you going to get? Here you get negative, and here you'll get a positive 4.6. Okay? So let's do this one dead center here. This one you knew before you came into this class, right? I mean, you probably knew most of this before today, but all right, so let's say your probability is 1/2 of success. Then your probability of failure is also 1/2. You have 50-50 chance. We use that all the time. That means 50-50. Those are your odds. 50-50 is a 1-to-1 odds. That's 1. And then the log odds is 0. The log odds is 0. Okay? So now we have this, and you can see the pattern. Probabilities range from what? If we can get smaller and smaller and smaller, and it will go all the way, the limit is 0. The limit here is 1, right? Same with 1 minus P. That'd be 1 to 0. Now the odds, you can see I can get smaller and smaller and smaller, and it will go all the way down to 0. Or all the way up to what? Positive infinity, and that's the exponential curve. And you can see the log odds can go all the way down to negative infinity and all the way up to positive infinity. And that's what we have here. Okay? That's exactly what we're saying here. And as you can see, this odds equals 1 plus odds is exactly what we're doing here. So for example, I mean, I could have written this, another way to see this is like, here, you have the odds is 1/2. I could have written 1/2, your odds is equal to 0.5, right? So now your probability is equal to what? Why is this the same thing? Well, you could say 0.5 over 1, right? So you could go 0.5 over 1 plus 0.5, and that's 1/3. It's the same exact thing. So we can go back and forth between probability and odds this way. I mean, we could have just said 1/2 over 1, and then our numerator would be 1/2, and our denominator would be 1 plus 1/2. So you can move back and forth. That's what you were doing intuitively, using this, and that's exactly the same thing as what we did algebraically over here. I'm just moving back and forth, and it's the same thing. It's just simpler to think of it this way for me. All right. Now, Do you want to spend a few minutes filling this out, or do you think you've got this? You have it for your homework, something like this. Do you want me to fill out any more of this? Do you want me to? Raise your hand if you want me to. Okay, I think you can fill that out on your own, and your homework is doing this. Okay, sound good? All right, now we can move on. So you know these, what this stuff means now, or you're familiar with it. Okay, so now we're back here where I inadvertently jumped to too quickly. And what we're going to do now is we are going to make predictions with the log odds equation. And the computer is going to make these maximum likelihood estimates. And we can look on page 181, where there'll be, we're going to talk about this much more later, but I want to show you, I want to work through it now. But let's look at page 181. And you should read what I say on your own. Basically right here, at the bottom here, this part right here, that the main difference between this ordinary, now we have this linear equation in log odds, and the main difference between ordinary and logistic regression is how we estimate these betas. Instead of minimizing the sum of the squared errors around our predictions, we estimate them by choosing the betas that maximize the likelihood of getting our sample data. And if you've taken step 400, or I'm sure you probably proved that, at least that's a big proof or one of those courses, that the maximum likelihood estimator is the least squares estimator when you're looking at ordinary least squares. But not here. Okay? And so maximizing this likelihood is the same as minimizing something called the deviance. We're going to talk about this more later. All right. So basically, this minimizing this deviance in logistic regression is analogous to minimizing the sum of squares errors in ordinary regression. So deviance plays the same role that the sum of squares does in ordinary regression. And we're going to be looking at something called an analysis of deviance table. We'll be, in this section, we'll be looking at that. And it's very similar to the ANOVA table in regression, extremely similar. So and here is basically what I said before, that we do this likelihood procedure because each individual point has its own value resulting in a 0 or a 1, own value of x. And so each point is, either log of 0 or log of 1. So, it's kind of crazy what we'd be doing here. So we're so we either have negative or positive infinities. So you could lump together points of about the same x and get that, like what we did, group them together and then get sort of the averages of the p's, like we did, like in a vertical strip, we could do that. But then our fitting results really depend on how we do those lumping for continuous variables. So we could still do this and it would give us a good fit like in the middle, but it wouldn't give us a good fit. When you're near 0.5, it would give us a fairly good fit like we saw, but it won't give us a good realistic odds for rare events. And maximum likelihood does. It's very sensitive to rare events, which is often what we're interested in. So we're going to pick these parameters using maximum likelihood estimation. So that's basically it in a nutshell. Now let's go back and look at this. So we're back on page 173 here. Okay, so back on page 173, and now we have this, the computer gave us this right here. It gave us this estimate for the intercept and this estimate for the slope in the log odds equation. And here we have this little analysis of deviance table with degrees of freedom and the model and the error. We'll look at this more later. And we have this sort of modified chi-squared statistic that we'll look at later. But for now, let's just work with this log odds equation and translate between. So this is in the log odds, and so let's translate and get what that gives us as a probability for getting into med school. All right, so we're just going to do this, work back and forth here go from the log odds to the probability, like that. Okay, so we can do that, and then we can use these regression estimates equation to predict the probability of getting to med school for these 3 scores that we looked at before. And for 10, it gave us a reasonable estimate of the probability, something like 60% or something. But remember, for this, it gave us a negative probability of getting in, and for this, it gave us a probability over 1. All right, so we can compare to those other ones on page 171 if you want. You'll see how this makes more sense using this equation rather than the previous one we got through least squares. Okay, so what are we going to do? So we're going to go through these 3 steps here. This is 1, and then 2, and then 3. So we want to use this regression equation in log odds to predict the probability, not of getting into med school. We want to predict so we want to do that. All right, so we'll start, it'll be this 3-step process. So we'll start with step 1, where we say what? The predicted log odds. The predicted log odds is equal to what? Negative 12.2 plus 1.276 times 10. And when I did that, I got 0.56. Okay? So that's the log odds. Now I want to anti-log that, right? Exponentiate it. To get the odds, the predicted odds is going to be e to the 0.56. And then I got 1.75. Now, how am I going to change 1.75 to a probability? That's step 3. Well, just think of it this way. This is your success. You can put a 1 here. This is your success, and that's your failure. So the probability is just going to be 1.75 over 1 plus 1.75. That's what I'm doing here. And it's what we were doing all along. Okay? And then we get 0.636 or 63.6%. And it even gives us a better estimate there than the other one did. All right, and you can do the same for all of them, and you'll see, like for this one, you could we'll just work through it with this. So here, our predicted log odds would be what? Our predicted log odds is going to just do the same thing. Negative 12.2 plus 1.276 times 6. And here we get a negative 4.544. When we know we see that negative, right, 50 log odds of 0 would be a 50-50 chance, right? Remember? Right here, 0. So when it's negative, we know it's going to be, the probability is going to be less than 50-50. Okay, so here we have that, and so now our odds, step 2, our odds is equal to e to the minus 4.544 equal to 0.0106. And then our probability, step 3, would be what? 0.0106 over what? Just add a 1 here, 1.0106, right? Which is approximately 1, what did I get? 0.0105 or 1.05%. Not a negative percent. Not a negative percent. All right, I think you can do this one on your own. How about if I just tell you the answer, what the probability is, and you can make sure you get it? It's going to be over 50%. It's going to be, I got P equal to 0.9965. 99.65% chance of getting in if you have that high BS score. Any questions? So this is just going back and forth between the different forms. And I've got a poster homework. It's there. I just have to unhide it, which I'll do immediately after class. So how about this problem? What if I asked you, what biological science score would give you a 50-50 chance? Like 6 gives you much too low, 14 gives you much too high. It's somewhere less than 10. This doesn't give you a 50-50 chance. It's somewhere, but like what would give you a 50-50 chance if we wanted to, if it was a continuous variable? Probably somewhere between 9 and 10, but what would it be? So what would give you a 50-50 chance? Well, your probability equal to 0.5 means odds equal to 50-51, right? Odds is going to be equal to 1-to-1 odds. And then the log of 1, the log odds, log of 1 is equal to 0, right? That's just back here, and this should just be immediate for you that you know that. Okay, and here we have that. So our log odds equation, we could just solve what would give us, what BS score would give us a log odds of 0. So our log odds is equal to 0. So 0 is equal to, where's our equation? This right here. So that would be equal to negative 12.2 plus 1.276 times the biological science score. So we just solve for the biological science score, which would be what? So the biological science score would equal what? Would equal 12 point. Did I copy this right? Yeah, 12.2 divided by 1.276. Sorry. And 12.2 divided by 1.276 is that. So 9.56 approximately, which is what we thought about. All right, any questions on that? Now, let's do one more chapter. We have some time. This is I just want to have you interpret what these slopes mean, what these in the log odds equation. All right. So what do they mean here? So we have this. Okay. So we have these S-shaped curves here that look like this, and here is when you have a slope. If it slopes down like this, when it's less than 0, that would be negative coefficient. We've just been looking at the positive coefficient here, but all right. So the sign of the slope in the log odds tells whether the probability of P, whether the probability increases or decreases as x increases. So the bigger, we just were saying the bigger your biological science score, the higher your probability of getting in. But let's say if it was the more you drink or something, maybe the lower your probability of getting accepted into med school. And then the magnitude of the slope determines the steepness of the curve. And the thing that you really notice, because it's bounded here and bounded there, is that the steepness varies. So it starts off gradual and increases really sharply, and then it goes gradual again. Okay? And so we have these three forms, right? So the three forms, they're equivalent forms. And if you look at this one, what does the slope mean? This says in the log odds equation, we have our regular slope, so it's just a linear equation. So it changes by a fixed additive amount, the slope does. I mean, the log of the odds changes by a fixed additive amount, right? It's a line. And here, you have this curve, like this. All right. So here, this slope changes by a fixed multiplicative factor. And that factor is what? If you go up 1 in x, if you add another, increase x by 1, that's adding 1 there, right? That is going to adding 1, it's beta 1 times x. So if you add 1, you're going to, it's the same as multiplying, adding, the same as multiplying by e to the beta 1, right? If I add a 1 there and distribute it out and then change this e to the beta naught times beta 1 times x times e, there's going to be 1 more if I add 1 e to the beta 1. So this is a fixed multiplicative factor of e to the slope, right? And here, so the slope changes by a fixed multiplicative factor. And here, look at this. There's no way to describe the change here. It's like if you, for example, if you increased your, right in the middle here, if you increased your score by 1, it makes a huge difference in terms of getting in. Where up here it makes hardly any difference, and down here it makes hardly any difference. So it really varies, and there's not a fixed way that you can describe it. Okay, so the odds form right here, this odds form, this one, yields the most intuitive and useful interpretation of the slope. Okay, so this slope here, 1.276 in the equation, in the log odds form, it's not very intuitive. Even though you like this line here, it's not very intuitive because for each extra point of the biological, the log odds increases. And that's not really, people don't, log odds is kind of hard for people to think in terms of, but in the odds form, it means that for each extra point on the biological score, the odds of getting into medical school are multiplied by e to that slope. That's what I was talking about, are multiplied by 3.58. And it's very useful. It's called the odds ratio. So this odds ratio is easy to interpret, and it's e to the beta 1. It's the multiplicative increase in the odds for 1 unit increase in x. So it means if you go up 1 point in your biological science score, that multiplies your odds of getting into med school by 3.58. All right? Does that make sense? What? No, they just get multiplied by 3.58. Not percentage-wise, yeah. Maybe if we do it, you'll see what I mean. Okay, so on the next page, let's see how we use this odds to compare the odds of individuals with different x values. All right, so let's do that. That's going to help you understand it. All right, so working through examples is always the best way to sort of cement these ideas in your head. So here we have the three forms of the logistic regression equation for our med school data. And didn't we already do this one, 10? We said, okay, so if your biological science score is 10, we plugged a 10 in here and we got 1.75. We did that right here on page 173, okay? So let's say right here, 173. All right, so we got that. And so now our probability of getting in, remember what the probability is just going to be odds over 1 plus odds. So that will be 1.75 over what? 2.75, which is equal to 63.6%. All right, so now let's say we went up 1 point. Now we could do it from scratch. We could put an 11 in there. But you see how if you just went up by comparing that to 10, it's just taking this 1.75, right? BS, if you add plus 1 there, right? That's just going to be multiplied. This addition here is the same as multiplying by e to that. So that's just e times e to the 1.276 times e to the slope. That's our 3.58. And it's our odds ratio. Why don't we put odds ratio is equal to e to the slope. This is our slope. That's what I'm talking about. And then that's approximately equal to 3.58. So the odds is going to get multiplied by 3.58, 1.75 times 3.58 to 6.27. So that's your new odds, right? And then the probability is going to be 6.27 over 7.27, which is about 86%. All right. So what if we wanted, let's say we just had 10 and now we wanted, let's say, what's the relationship between 14, let's say? So if your odds, let's say you knew your odds were 1.75, and now that's 4 points higher, so we'd say 1.75 times e to the 1.276 times 4 times, which would just be the same thing as multiplying by 4 here, right? And so then that is equal to 288.2. So if this is your odds of getting into med school. So what would be the probability then? It would be 288.2 over what? 280 what? 9.2. Okay? Which is 99.65% about. Does this make sense? And if I wanted to compare this one, I could just multiply this one by 3.58. If I wanted to compare it to like 15, let's say, then I would just multiply, you understand, right? If I wanted to I could just say, okay, 288.2 times e to the slope, because it's just a 1 point difference. And here I would get 1,000, that's huge odds. But you see why it approaches 100%, but it's never going to get past 100%. because you're always going to have one more in the denominator. And that's 99.9%. So this odds is kind of confusing. There's a lot of different terms, but this odds ratio is talked about all the time. And it's the multiplicative change in the odds for a 1 unit increase in x. And it's greatest, okay, so that, the change in probability, you can't describe as a fixed anything. The change in log odds you can describe as a fixed additive factor. The change in odds you can describe as a fixed multiplicative factor. But the change in probability you can't describe. You can't describe it in a fixed anything. This is an important point. I should show it to you. So let's just go. It's interesting, too, because it applies to lots of different data. OK, so we go back to here. This is our actual curve here. All right? So on page 168. So what I'm saying is you can't describe the change as you go from 1 point increase in the biological science score. How could you describe, you can't describe it as in terms as a fixed multiplicative or additive change in the probability. Why? Look at this. Look how right in the center here, a 1 point change. This is where it's steepest, right? In fact, it's going to be steepest right here at 0.5. That's where it's absolutely the steepest. And so a change makes a huge amount of difference here in terms of getting in terms of your odds. Out here, it makes hardly any difference. And those of you who worry about your grade point, the tiny, or you're trying to improve from a, 35 to a 36 on your ACT, or just trying to, or way down here, and hardly a 1 point difference isn't going to affect things. Because you're almost guaranteed to get in up here. If you're super, super high, and you're almost guaranteed to not get in down here. And 1 point doesn't hardly make any difference. But like if you're right in the average of the people applying, or right in the, like where you have a 50-50 chance, that's where the 1 point difference is going to make a huge difference in your acceptance. So the probability of you getting in. So it really affects things right here, but not if you're already very likely to get in, or already it's going to be very hard for you to get in. But if you're right in the middle of where they're making a decision, well, then a 1 point difference is going to make a big, will make the most difference in your probability of getting in. So that's the idea here. And that's true of it's true just because of the shape of the logistic regression curve. So, so how does that affect things? So let's do a problem where that comes up. Where does it come up? Okay, so here's a good example. All right, so let's just do these problems. All right, so two people have a 2 point difference in their biological science scores. Compare their odds of getting into medical school. The person with 2 point higher score has what times chance, not greater, I'm sorry, greater odds. These are all odds. Okay, so what's the answer here? 2 points for each point difference. Your odds are increased by a multiplicative factor of e to the 1.276. So you're going to multiply. That's the same. Should have given you another option, which is just arithmetic. It could have been e to the 1.276 times 2. That also would have been circled, right? And there's another one. This is also the same thing because e to the 1.276 is approximately 3.58. So these three are the answers, with all equivalent forms of the same number. Okay, now what if there's a 3 point difference? What would we fill in here? What would we do? It would be what? 3 point difference between, it doesn't matter what their score is. is going to increase the same multiplicative amount. The odds are going to increase. The person with a 3-point higher score has an what? E to the 1.276 times 3. That's e to the 1.276 times e to the 1.276 times e to the, which is equal to about 46. And what if I said the lower? Then it would be 1 over 46 times, right? It would be negative 1. That would be the relationship. You divide by 46 instead of multiply by it. So if two people have a 3-point difference in their biological science scores, how do their probability of getting to medical school compare? Think about it. You do not have enough information. You can't describe it. Not enough information because it depends, not enough info. You know the odds ratio, right? The ratio of the odds, but you don't know the odds because or the probability. You just know the ratio. If you knew the odds, you could get the probability. It's just odds over 1 plus odds. You don't know the odds. So you don't know the odds, so you don't know the probability. You just know the ratio of two odds. How much more, So you don't know the probabilities. You'd have, what piece of information? You would have to know you'd have to know x. You'd have to know where on that curve they are, right? To change, because you'd have to know where they are. Here, a 3-point difference is not going to make much difference. Here, it's going to make a huge difference. Here, it's not going to make much difference again. You have to know where along here they are. Okay. So you just know the ratio of the two odds. You don't know the odds. Now I think that's, let's see, is that all we're going to do for today? I think that's all we're going to do for today. Let me just make sure we covered everything. Yeah. Okay, so I'm going to open up your homework right now. And if you have any questions on any of this, just come up and see me.